Welcome back. Good afternoon. Today we have the pleasure to have Anna Brandenberger from MIT. She's going to talk about errors and correction in cumulative knowledge. Please.
Cool, thank you. Can you hear me? Is it on? Cool. Okay, thanks everyone. So today I'm going to talk about, as she says, errors and correction in cumulative knowledge. So this is a kind of fun model that I'm going to introduce, and it has to do with what we call cumulative knowledge. So what is this? The question that we're kind of asking when we're talking about this model is societal knowledge robust? So what do we mean by societal knowledge? This is kind of, you can think of like what we're doing, right, as math people. You're like, there's some body of theorems and you're adding to this. There's some sort of societal knowledge. You can think of like science in general. You have this like growing body of knowledge where every time you create something, you kind of depend on the correctness of what you're like building on, right? Another example is like software packages, but there's a bunch of things like this, right? So the literature that we're thinking of is these kind of error-prone processes, where one such example is error broadcasting, where this literature, it's kind of a pretty wide literature, but it considers you have some sort of tree structure. It can be a tree or a DAG or anything kind of with acyclic but directed. And you start with the root that has one bit of information, and you propagate it down along the edges, where each edge has some sort of Markov kernel, where essentially with probability p, some small probability, you flip the error, and then, you flip the bit that has been transmitted to you. And so as you propagate down the tree, you're kind of losing information. And in this setting, the questions are usually like, at some level n, can you recover? Can you do some sort of root reconstruction? So it's called kind of root bit estimation or root recovery or this sort of literature. So in this literature, you have basically only one bit of information or some information, and you're propagating it, and you see how much you can recover. And what we're thinking about in our setting is like, what if, like in science, you're introducing new results, right? Every step, you're not just trying to propagate. You're trying to introduce something new, and then also building given your prior knowledge. So for example, if like I'm writing a new paper, I write a theorem, and I rely on the result of Gabor. Gabor's result better be right for mine to be right, you know? So this sort of question. And these steps that we add can propagate errors, right? So as a tree builds, you can have these errors propagating more and more. If, for example, some influential paper was wrong, but just keeps kind of growing children. And so we're hoping, you know, for science or math to be correct, which we hope it is, for there to be some sort of natural error correction occurring. And these are the types of processes that we study. And these kind of occur in society because things grow slowly, you know, you rely on prior results. And if, for example, an error gets introduced, like it happens, so we see there's some example, for example, from like in the early 1900s, there's some paper by Lebesgue, for example, claiming that a projection of a measurable set is measurable, and then like 10 years later, some Soviet mathematicians came up with actually this is false, and here's some like new branch of descriptive set theory that covers this. Recent news, there was some like Alzheimer's research, a big like scandal of a lot of it being wrong. So there's some of this stuff that like vaguely applicable, you know? And so these errors, as I introduced, can have some widespread impact. So even suppose in like the sub-DAG of like this false guy, this guy could have not made any mistake, but since it relies on a false node, it spreads the error and so on, and it grows. So our question is, what can you do with local checks? So you don't want these checks to take up too much effort, because you know you want to spend most of your effort on deriving new results. So this is kind of the motivation of the problem. So for the remainder of the talk, I'll talk about this probabilistic model that describes this phenomenon. And then I'll formulate the goal that we have, which is we want to have some sort of error elimination with not too much effort in terms of this locality. Then I'll talk about some of the results that we have in this direction, some proof ideas, and some open questions for everybody. I see Roberto's not here to stare at people, but it would satisfy him. So first, let's talk about the model. So cumulative knowledge processes consist of 3 components. So first, you have a growth model. So as I alluded to with the picture, the knowledge state is represented as a DAG, where units represent new knowledge. And these are labeled DAGs, where the label is essentially whether the unit introduces an error or not. And so the growth model essentially represents, like, we have some probabilistic model for how this grows at every step. Then you have some error injection, where at every step you could potentially introduce an error. And we allow for either probabilistic, so with some small probability you make a mistake, or some adversary could also act with small probability. And we also have some sort of error checking mechanism. Because suppose you didn't have an error, suppose you didn't have any checks, right? Then with some probability you create some errors and then they just like propagate forever and your system, you know, just is wrong or has a like large fraction of wrong states. So these, the question we have is like, what kind of error checking mechanisms can we study and what kind of error checking mechanisms like make sense and are local, and so forth. So this model was first introduced in a more limited setting in this paper here by Ben Lilizer, Mikkelinser, Mossel, and Sudan back in 2023. They consider it in a much less general setting. So when I describe the more details of the growth model and the error injection and so forth, I'll explain kind of what they did that is slightly simpler. So the growth model. So the state of the system at a time t is described by a labeled DAG, where the labels essentially represent your state, your truth value. So the labels are CF, CT, and PF, where CF represents conditionally false. So you like inject an error in this node. So this is this red guy up here. And CT means true conditioned on your ancestors. So essentially a node is true if it is CT and all of its ancestors are CT. So essentially all of these guys here that are in the subdag of the red node, despite themselves being CT, they're actually false because they rely on something false. And so the question we're investigating is kind of how much do these propagate, right? How much does the effect of this false node, of this CF guy, propagate down the tree as the system evolves? So you initialize with some state G0. Usually you can think of just like some true node, CT node. Most of our proofs are general enough to you can just initialize with any state of the system at some time, with some like CT, some CF nodes. And actually, wait, one thing that's important to mention back here is that both CF and CT nodes, these are kind of private states. So unless you do some sort of checking, you don't reveal what the state of a unit is. So what we mean by PF is suppose you do a check and you reveal that actually like this node and this node are both false. Then you can mark them publicly to be false and then no more nodes will connect to them. So that's what we mean by PF. And both CF and CT mean publicly true. So both of them are PT. Is that clear?
So if you check a node and you don't find an error, then
you don't do anything.
It's not becoming proclaimed true.
It's not. Well, it is still proclaimed true in a sense. Because as long as a node isn't proclaimed false, it is proclaimed true.
It may be rechecked again.
Yeah, exactly. It may be rechecked again. Yeah. Okay, so you initialize with some state, and then, okay, what do you do at any new step, right? So you have a current state at time t, and at time t plus 1, what you do is you add a new node. You have some parameter, which is the number of parents, m, and you draw m parents, each from the existing DAG with probability proportional to some function a of the PT out degree. So A is just your connection probabilities. And we think of like some general class of functions, A, that are just like regular in some like Lipschitz sense. So their like growth is bounded from above and below by some constants, and our like theorem will include some sort of bounds on these that you require. These encompass like the usual things you would care about, like preferential or uniform attachment for specific settings. So if A of D is just D plus 1, you get the usual like preferential attachment. And if A of D is constant, you get uniform attachment. Okay, so in the previous work by Ben-Eliezer, Mickelenser, Mossel, and Sedan, they made specific settings for each of these parameters. So they considered the tree-like, essentially the preferential attachment tree, where A is set to be D plus 1, and M is set to be 1. So then you don't get this kind of DAG structure, you just get a tree. Yeah. Okay, so now for error injection. So we've created a new node, and now essentially you have some epsilon error rate, so you flip some epsilon Bernoulli to decide whether your new node is CT or CF. So with probability epsilon, you inject an error. And another parameter that we allow is actually an adversary. So all of this that I just described, you actually run with probability 1 minus q. And with probability q, you instead just let an adversary do whatever it wants, just with bounded influence. So it adds a new node with arbitrary truth value, just like connect to some number, some bounded number of parents. Okay, and importantly, as I mentioned, the errors are hidden at birth. So when you create a new node, if you don't check, you just add it to the graph, and so it's like publicly true. So now checking. So when you add a new node, you also do some sort of checking process with some probability p. So this is essentially the checking probability. So I added this new guy, and with probability p, I'm going to check in a k radius. So our results allow for some broad class of checking mechanisms, but for the purposes of this talk, you can just think of like doing a breadth first search in a k radius up until you find a false node. And then when you find a false node, if you find one, then you can mark as PF all of the guys that depend on that guy that you found. So you can mark all of these as PF. And then these essentially stop having children because they've been marked. Okay. In this case, we're not done. This false node U that was up here still has some influence. So its subdag still has some alive nodes because these nodes depend on it, and they're still CT, so they can keep having children. And so this process can keep growing. Okay, so combining, you have all of these parameters, and essentially at every step, if you're non-adversarial, you add a new vertex according to some attachment probability. You flip a Bernoulli to determine whether it's true or false, CT or CF, and you flip another Bernoulli to determine whether you check. And obviously, if you add a CF node and you check, you just find that yourself, you're false, and you remove yourself, and you're done. Okay. Any questions about the model so far? Cool. Okay. So now I'll talk about the error elimination goal. So what do we want? We kind of want some sort of error correcting style bound. So an analogy with like information theory, to give you a style of the theorems we want to show, is that like in that setting, right, you're encoding some sort of message over a noisy channel. And the channel has some noise, you send your message, you want to send k bits, so instead you send n bits with n over k, hopefully some constant. And you want B to be able to decode your message, right? And you want this factor of increase to not be too large. And the answer is yes, you can do this. So the analogous question in our setting is, can you guarantee that the fraction of true nodes is omega 1? As in, can you guarantee that the fraction of false nodes that are still alive, as in that are still marked PT, considered true, goes to 0? And we want this to be for a constant rate of errors, for p less than 1, so you don't check every node, because obviously then things are going to work, and for a bounded locality. So you spend a bounded amount of effort per node for these checking processes. And so the answer, essentially the rest of the talk is going to be saying yes. In a robust sense, for this family of models, you can do this. But also, we have some results in the other direction saying that it's non-trivial, right? There are some settings of parameters, for example, if epsilon is too small, that you will not be able to root out all the errors. So formally, we define error elimination to be for every CF node in the DAG, there exists some time for which all of its descendants are marked PF. So all of its descendants are essentially caught, and its subdag stops reproducing. So this is essentially what it means. So you have this node U, and at some time, all of its subdag here is marked PF and stops reproducing anything. Error survival is essentially error is not eliminated. So with positive probability, you have some false node whose subdag survives forever and grows. Okay, so in terms of results, we have a general error elimination theorem which says that essentially, if you have an adversary that's small enough, then essentially for any settings of parameters, if your adversary is small enough, then if you check with high enough probability and in a high enough locality, then you will be able to eliminate all the errors. That's essentially what this is saying. And I will go into a little bit of the details of the proof when I talk about the proof details, let's say. And to give you a sense of the numbers here, we have concrete numbers that for the threshold of P and K for which you actually have error elimination, but they kind of depend on epsilon and all the other parameters. But if you want to just think about the tree-like setting with preferential attachment, where you have no adversary, then essentially there, if you check in a radius of 4 or more, you can check with there's some threshold of P such that the errors will be eliminated. So you need to check your parent, your grandparents, and 2 more in that tree-like setting. Okay. Now for error survival, this is the bad news, right? If k equals 1, so if you only check your parents, and for any probability, less than 1, the errors will survive. And similarly, if p is less than epsilon, so if your checking rate is less than the rate of occurrence of errors, the errors will also survive. So I'll give you a proof of both of these actually when I talk about the proofs, because they're pretty easy. And the proof of this p less than epsilon is how our more general theorem regarding error survival is proven. The methods carry over. So one other setting where errors survive is if you have unreasonable attachment functions. So for example, if your probability of connecting to some specific d is 0, then you'll have, if it has some hole in your distribution, then it'll be very easy to propagate the error forever because you can just initialize the graph in a bad way with some positive probability. And similarly for if you have some growing very fast attachment function. So now the more general theorem is that you can actually beat the p less than epsilon, or beat in the sense that in all settings, or in most settings, even if p is greater than epsilon, there are some p's where the error effect will survive. And this is for any k. Okay. And another interesting result that the previous paper showed in the tree-like setting is that in this preferential tree with no adversary setting, is that if you check in the depth 2 radius, so if you check your parent and your grandparent, then actually for any p, the error effect will survive. So in this tree-like case, you have that if k is greater or equal to 4, you can eliminate errors, but if k is equal to 2, actually you cannot. And the proof is pretty interesting. If I have time, I'll tell you about it. Okay. So let's go to some proof ideas. I will go to the board. Okay, so I'll attempt to write big. Let me know if it's big enough. Okay, so let me first talk about this. Actually, let me go back let's go back to this. So let's first talk about k equals 1. Is this big enough? Okay, cool. So here, why do errors survive? This argument is very simple. Just initialize your configuration with something like this, where this is a false node and this is a true node. So here, the entire DAG is false. And with positive probability, when you add a guy here, you will do a check, mark this as false, and from now on, you propagate, and the errors cannot be caught because every time you add a new node here, so now these are marked PF, so they no longer gain any children. So every time you're going to connect in the subdag of this guy, and you are never going to go higher, and your errors will propagate forever. Cool. Now for p less than epsilon. Okay, so here, the proof idea here kind of gives you an idea of how we prove the rest of our arguments. So because this model is quite like non-monotonic, we have very few structural results about the DAG. So for example, the height, the degree distribution, things like that we have very little control over. So all of our results kind of build upon you find some sort of potential that behaves in a nice way, like a super martingale or a submartingale, and that proves your result. So essentially, here we want to show that for p less than epsilon, the error survives. So we want to show that there exists some node u that is CF that in the DAG, such that its subtree, so it's PT subtree view, which is false because it relies on this u who is false, survives forever. So we want to show that this is positive for all time. And how do we do this? We essentially design some martingale. So we define a phi t of BTU, which is going to be less than this, less than the number of nodes in the subdag, such that this is a, let's see, we want it to be a non-negative submartingale. And so essentially we want this guy to be positive for all time. And the fact that it's a non-negative submartingale will prove this part of it. Essentially, you can just do some like bounded differences and show this pretty easily, just like standard arguments. So essentially what we want to do is design a non-negative submartingale. Okay. And so our choice that we'll use to prove the p less than epsilon bound is essentially just pick phi of GTU to be the number of minimal false nodes. And by minimal false node, I mean either a CF node or a child of a PT node, of a PF node, sorry. In the sense that these are kind of minimally false in the sense that they're false and they're like closest to a false node that has been, that can be detected. Okay, and to show that it's a submartingale, essentially you just compute the expected change at time t as you go from t to t plus 1. Can you see down here? Okay, cool. And this essentially, it's upper bounded by, so you want to show that this is positive for all time, right? And what you do is essentially, so with probability 1 minus q, you're at a non-adversarial step, right? And so here, with probability epsilon, you add an error. And with probability p, you check and you remove that error, so there's no difference. And with probability 1 minus p, you don't check, and so that error is added, and so you have a plus 1. And then with probability 1 minus epsilon, you add a CT guy, and with probability p, you do a check, and that's the only thing that can remove errors. So here, and you remove up to 1, and so you have this expression, and essentially if you simplify this, you get that this is positive if p is less than epsilon. Cool. Right, so that shows this p less than epsilon bound, and this holds for any k, right? And our more specific result for like a threshold that can exceed epsilon is essentially by following the similar flavor of argument where you try to find a submartingale that lower bounds the number of CF of like sub nodes in the subdag of some CF node U. And you design a submartingale to not just be the minimal false nodes, but also the leaf nodes, or some like function depending on the leaf nodes, because in some sense the leaf nodes will propagate the error because at every time step you're going to be adding a new leaf, right? And so they're going to be like furthest from like nodes that can be checked and found easily, and there's one added at every step. Okay. And now for the elimination idea. So here it's a similar type of proof that we are looking for. So, but now instead of a submartingale, we're looking for a supermartingale, right? Because we're trying to show that for every U, CF, you want to show that GT, PT of U, its subdag goes to 0. And so what you do here is you design some phi that upper bounds the number of nodes and has this property. And we want phi to go to 0, and we do that by designing it to be a supermartingale. And what's the idea for our phi that we pick? We essentially have, okay, so let's draw a picture here. you have U, and you have its subdag here. And you have a bunch of nodes in here. So for instance, some node V. We want a potential that's going to be summing over all the nodes in the subdag. And it's going to be essentially every node will contribute exponentially in the distance to U, or to its nearest minimal, or its nearest CF node. So, or minimal false node, depending. But essentially, it kind of represents how hard it is to remove this V. So the potential is going to be, if you let this be the distance to your nearest false node, then this is going to be A of the out degree of V. And this represents just how much influence this has in terms of its degree. And then some constant to the power of V. Some constant greater than 1. And now we want to show that the expected change at every step is going to be small, so is less than 0. And this we essentially show in a similar way by analyzing cases. And the idea is that suppose you add a new node. Okay, actually, add new node. And suppose you don't check, or you don't check successfully. Then what you're going to get is you're going to get a new contribution from this new guy. That's going to be something like C to the distance of W to its nearest false node. But this is going to be at most like a constant factor of the existing potential. So like some C times phi. GT U. And so this is going to be added. But suppose you do check successfully. Then, okay, suppose that you check this node successfully. Then all the nodes that have V as their nearest false node are going to become one closer to a false node. And so you're going to get a multiplicative decrease again here. So here you're going to get a negative like C prime phi. And then by setting your parameters correctly, you can kind of optimize. You can optimize these and then figure out that like it's gonna be what you want. Oh, and also if you add an adversary here, it also has like bounded influence, and so it's also going to be just another constant factor of the existing potential. And this is why, so actually, intuitively, you should think that the adversary, like the worst thing it can do for error elimination is actually to take a subdag that's false and then add a true leaf very far. So it's going to grow this structure, but like something that's hard to find, essentially. So this is also the same. So plus C phi. Okay, cool. Awesome. And then maybe I'll give a brief note about what this other survival proof is. So I'll give a brief note about this final thing, which is quite interesting. So here, essentially, what they do in this case, so they have a tree right here. So maybe I should erase. I can go here. Is that visible? Cool. I'll just say some brief things. So here, the idea of proving this is you set, you have some p less than 1 of checking, and essentially what you do is you are counting the number of occurrences of structures that look like this. So essentially, you're looking for things that are like 2 nodes of degree 1 that are both CT, and then maybe some CF thing above. But essentially, these things are kind of going to block your checks. Because when you kind of connect, you check your parent and your grandparent, right? So if you connect here, then you're going to check this guy, and you're not going to reach what's above. And so the intuition here is that they grow the tree, they initialize it in a nice way, and then they argue that by the time you've checked the first one of these, so you like initialize it with something like this, and then you like grow. And by the time you've removed this guy, let's say check this, or let's say check these, and these become false, then the number of similar structures in here, which has grown to be large, is going to grow to infinity, and then you can repeat the same argument you had at the beginning for each one of these. And that's kind of the intuition for what's going on here. And since all you need is just 2 nodes of degree 1, where one is the parents of the other, it's like very easy to have the structure appear. And there's known results for like the preferential attachment tree on like how many of these appear and so on. Yes?
A question about this slide. So you say in the lemma, errors survive, and in theorem you say error effect survive.
Oh, sorry, same thing.
It is the same.
Yeah, it's the same thing, sorry, it's just.
Okay. And when you say errors survive, that means for any fixed error, eventually in time you will go back and correct it?
No, sorry, other way around. Error survives is that you will not be able to correct it. So for some error effect, some error guide, its subdiag will grow forever.
But you don't, so
with positive
when
probability.
you correct, that's always like error specific? Do you have results that somehow say like uniformly when time is sort of far enough out with high probability you get all or a
Right. So yeah, so this type of result kind of implies it implies a bound on like the fraction of nodes in your graph that are erroneous, but you can't really get any uniform bounds because essentially at any point you could create a new error, right? And so you can't really say that there's no errors like at any fixed time. You can only say like the effect of this one error dies. But yeah, we do have some bounds on like. Yeah, these bounds imply some on the number of false nodes at any time. Yeah. Cool. Awesome. Now I'll go to some open questions, also to satisfy Roberto, who's not here. So first is, as I briefly alluded to, we don't have a tight understanding. So there's a question of whether there's a sharp threshold between error elimination and error survival. So for example, in this tree case, you had that if you check only your parent and your grandparents for any p, like even if you check super often, you will not be able to eliminate all errors. But for a k greater or equal to 4, if you check frequently enough, you are able to. And the case of k equals to 3 is still unclear. So that's open, and it would be, so the question is there something sharp there? And on the way to that, there's also even simpler, in order to prove some sort of sharp threshold, you would need monotonicity to begin with, right? So you would expect that, suppose you increase p and k, so you increase your checking probability and you increase your depth, then it should be easier to eliminate errors. So you should have that for like specific settings of p and k. You increase them, you should, if you have elimination, you should still have elimination. And this we don't have, except for a really simple setting, which is like very, very simple, which is like you have just the tree, so m is equal to 1, and you start with a CF node, and everything else is true. So essentially, the entire DAG is false, and the question is just, can you remove it? So in this case, epsilon is 0, and q is 0. But for any general case where you have some positive epsilon, so you start with some true guys, and then you have some positive probability of injecting error, we don't have this sort of monotonicity result, which seems true, so it'd be nice to prove. And then, as I alluded to earlier, we also don't have much structural information. So we would guess that suppose you start with a preferential attachment tree, suppose that you like have a really high probability of injecting errors and checking, then you probably lose some of the preferential tree structure, like degree and height and stuff, but we don't have any results in that direction. Cool, thank you.
Do you have questions for Anna? If not, let's thank Anna one more time.